In this video, we're going to graph some endothermic and exothermic changes. Lots of graphing in this chapter, huh? Okay, so we're going to look at this graph of reaction progress, which is kind of like time. As time goes by, the reaction progresses like time. And along the other axes, it's probably going to be labeled in like joules or kilojoules. Maybe we'll go kilojoules. Some kind of energy value. So this is a graph of energy changes over time. It's probably numbered. So maybe we can say like, maybe 10, 20, 30, 40, 50, 60, maybe something like that. All right, so here is an exothermic reaction. The exothermic graph, let's start at maybe around 40 kilojoules. It's going to dip up, and then it's going to drop down. I'll bring it down, maybe right in here. Oh, that's lovely. That's a nice graph. Now there are some things that they want us to label on these graphs. First, the reactants and the products. The reactants are always at the beginning, and the products are always at the end, regardless of the energy level. Activation energy is this little boost of energy that it takes to get a reaction started. It is this little quantity up on top. This is your EA, activation energy. So for this particular reaction, I just kind of arbitrarily threw some numbers up there. We would say that the reactants start at about 40 kilojoules, and up on top, this peak is where there is sufficient energy for a reaction to occur. Okay. So this is sufficient energy up on top. The reaction to occur, and then it progresses spontaneously, releasing energy, which is why my products are at a lower energy level. We released energy to the surroundings. Alright, so the last delta H value that we'll look at is this delta H Rxn, which is really just the energy change for a chemical reaction. It's the difference between the heat energy of the products and the reactants. Products minus reactants. That's not so bad. See, if I mark it in on this graph, it's kind of like this difference here. The difference between the energy level of the products and the reactants. That's my heat of reaction. If I want to calculate it, you just plug it in. Products minus reactants. So let's say maybe 10 minus 40 is negative 30 kilojoules. There'd be my heat of reaction. There's a net release of 30 kilojoules. Notice that the overall energy change for the reaction, the heat of reaction, does not include the activation energy bump. Common mistake. Here's kind of the deal. So we have to add a little energy to get the reaction started. So yeah, I needed to input this 40 up to 60, 20 kilojoules of energy. For this particular reaction, I need to add plus 20 kilojoules of energy, which, that really is my activation energy, 20 kilojoules. When you finally get to the point where there's sufficient energy for the reaction to occur, as you start forming new bonds, you immediately start releasing energy. So we're going to start releasing energy. And eventually we kind of get back to where we started. So we're going to get 20 kilojoules back. So that really they kind of negate each other. I had to add 20 to get the reaction started, but then I get the 20 back as I start forming new products. Wipes each other out. The heat of reaction is really the net change, not including the activation energy. Yes, I added 20 kilojoules to get it started, which is very important, but I'm going to get that back along with this. Then I'll also get a net release of another 30 kilojoules. So here's my negative 30. That's the overall change for the reaction. So we do not include the activation energy bump when we want to know the total energy change. And that's kind of a common mistake where people think like, I don't know, maybe it's like high point to low point. Nope, just difference between the products and the reactants. Alright, so let's do the flip side, the endothermic graph. The endothermic reaction kind of looks like a mirror image. Alright, let's see how good I can draw this. Let's say we kind of keep the same axes labels. And then this one would go up. Oh boy, and then down a little bit. That's not bad. Maybe I'll make this drop a little bit more. Maybe I'll make it a little bit lower. I'll try to kind of keep it similar to the other one. So that this maybe goes down. Oh gosh. Close enough. Okay, so we're going to label the reactants and the products. Reactants at the beginning, products at the end. In an endothermic change, the products have gained energy, so they should be up at a higher energy level. The heat of reaction is still the difference between the reactants and the products. Delta H RXN. But this time I should get a positive. Let's say that my products are around 40. I'll try to use like the same axes as both graphs. Minus my reactants at 10. Now I'll get a positive 30 kilojoules. Excellent. Yeah, it's endothermic. It should be a net increase in energy. The biggest difference is the activation energy. Because again, we mentioned that way up at this peak is where we have sufficient energy for the chemical reaction to occur. Well, in the exothermic reaction, your reactants are already at a pretty high energy level. But now in the endothermic, my reactants are starting in the pits. They're already at a low energy level. I need to add all of this energy to get up to the point where I have sufficient energy for the reaction to occur. It's all of this. That's your activation energy. So it really is like from 10 all the way up to 60, 50 kilojoules. Activation energy for an endothermic reaction is always pretty substantial. It'll be a lot higher than the exothermic version. And so again, I mean, there are some things that are kind of interesting. So we add all this energy to get up to the peak, where I have sufficient energy for the reaction to occur. And whenever you start forming new bonds, I mean, the new bonds should release a little bit of energy. So yeah, we'll release just a little bit when we form the new products. But there's still a net gain in energy. Ah, yeah. So I mean, if you kind of think about it as, here I had to add 50, and then maybe I get 20 back when the new bonds form. But there's still a net gain in energy. There's still a net gain in 30 kilojoules. So that's kind of like your overall energy change for the reaction. Now the only thing that we should mention, the only other thing we should mention about these adorable little graphs. There it is, a catalyst. You've heard of a catalyst, something that makes a reaction go faster? Yep, it does. Here's how it works. Let's say I got a reaction. I could make it really endothermic or exothermic. We'll go with an exothermic. And maybe for this particular reaction, here's my activation energy. So this might be my activation energy without a catalyst. A catalyst makes a reaction go faster by lowering the activation energy required to get the thing started. So if you don't have to add as much energy to start the reaction, it should go a lot faster. So maybe with a catalyst, my graph might look something like this. And then maybe this would be my activation energy with the catalyst. With a catalyst. So if it takes less energy to get the reaction started, it should go faster. Catalysts work in different ways. Some of them add energy themselves. Some of them kind of form a place for particles to congregate. So if we can bring the particles closer to each other, they're more likely to react and collide with each other. And then maybe I don't need as much energy to push and force the particles close to each other. But this is kind of the main reason why catalysts make reactions go faster. Less energy is required to get them started.